I'm Shuhei Masuda from Jamstack. I will present our activity of BGC Argo. The title is Perspective Global Ocean State Estimation by using BGC Argo data. So there are many global ocean issues. For example, ocean acidification is very prominent in the recent years. The left-hand panel shows the distribution of pH in 1990 and 2016. You can see apparent increase of pH value in the global. And the right-hand side shows the net primary production, distribution, and trend in global ocean phytoplankton productivity and chlorophyll values. In the recent years, after 1999, the values is decreasing in the globally, and the main cause of this decreased trend is caused by the decreasing in low latitude area. In addition, carbon cycle is changing. The figure shows time series representations of global ocean CO2 uptake from 1990 to 2019. The upper panel shows monthly net CO2 uptake, and lower is annual net CO2 uptake. You can see after 2005, the value gradually increasing. This shows the ocean uptake is enhanced in the recent years. This is a very important aspect of global warming because the uptake is closely related to the global warming and its future. And to resolve these issues, there are 3 steps. One is to grasp the past current status of BGC parameters. For example, dissolved oxygen, nitrate, pH, with physical parameters, temperature, salinity, sea surface height, and so on. And the second step is better understand the mechanism of ocean changes, because if we don't know the mechanism, we can't forecast any of the future. So on the second part is very important part for the BGC research. On the basis of 1 and 2, we can forecast the future of ocean. For the first step, the algos are promising. Algos mean the conventional algo float and deep algo, BGC algo, and mixed algo. The core algo, as you know, resolve many issues of physical oceanography. For example, global mean sea level change, ocean heat storage, and so on. And BGC Argo array has huge potential to provide the current status and temporal development of the aspect of ocean acidification, change in carbon cycle, and net primary production, and other issues. The right-hand side panel shows the distribution of BGC Argo in recent days. The number and quality of BGC data will get enriched in the near future by increasing BGC Argo and also with high-quality shipboard and satellite observations. For the second step, ocean state estimation is very promising. We intend to clarify mechanism of global ocean change revealed by observations, ocean acidification, changes in carbon cycle, and net primary production. The physical and BGC observations should be integrated into one dataset on a unified framework because the individual data is very important, of course, but sometimes the cross-correlation of parameters is very important and vital to know the mechanism. For example, the change in BGC parameters sometimes depend on the physical oceanography. A data synthesis using a numerical model with a smoother type approach is better because dynamically self-consistent dataset is very suitable to analyze the mechanism because the model formalism is take advantage of such analysis in BGC research. So in this presentation, here we show an example of global ocean state estimation data synthesis by using BGC Argo data, focusing on its possible impacts. We use a framework to integrate observation as below. For physical parameters, we use conventional ocean general circulation model and assimilated data. Synthesized data is sea surface temperature, subsurface temperature and salinity, and sea surface height anomaly, and ocean mixing. These data include Argo, GO-SIP, shipboard data, and also some buoys and so on. The assimilation scheme is for the bar, a kind of smoother type data synthesis. For BGC parameters, we use this NPDZ model, and this is on the basis of left-hand side ocean physical ocean field. So the variables is connected with physical and BGC parameters. And assimilated data for BGC is monthly mean nitrate, surface chlorophyll A as phytoplankton, and net primary production. The assimilation scheme is Green's function. It is a simple type data synthesis approach through the parameter optimization. I will discuss about this scheme after that. This is an example of observation data, Argo data, remote sensing data, and shipboard data. You can see these observations provide a very beautiful view of the ocean. But this dataset is cannot provide a mechanism or physics as itself. So we try to deduce the more information by integrating these data. Here is BGC Argo data we use in this research. In this research, we use only oxygen data because this is very first step of our research, and following this research, we plan to integrate other data, nitrate, backscatter, and so on. For the BGC Argo data, we have prepared two sets of datasets. One is BGC Argo from 2002 to 2012. The other is 2002 to 2020. The right-hand side panel shows number of profiles. You can see the number is increasing linearly from 2000. And these two datasets is used independently in the two data synthesis experiment, so we can evaluate the impact of number of BGC Argo. Here I will explain the Green's function approach briefly. This is the schematic view of the scheme. The horizontal axis is time. The vertical axis is model variables, for example, temperature, salinity, or DO. And this red line shows one model result time trajectory for parameter B equal 1. The dark blue line shows the parameter B is 0. These two cases is carried on independently, and the observation is only 1 point time this green cross line, cross point. And you can see in case B equals 0, the result is close to observation. And in case B equals 1, the difference is very large. So this system answer in this case maybe B equals 0.2 is the optimal, and the same parameter study will be done for a model parameter A equals 0 and A equals 1. These two independent model calculation is done, and then evaluates the difference between the model result and observation. And you can see in case A equals 0 and A equals 1, the difference between observation and result is very similar. So this system answer both is not so good, not so bad. So the optimized value is in this case A equals 0.5, B equals 0.2. And then we recalculate the synthesis experiment with these parameters, optimized parameter. The result will be close to observation. And this is the approach of data data synthesis by Green's function approach. Of course, the package is more complicated, and the evaluation of the optimization of the values is more systematic and statistically valid. Here is the implementation of our optimization experiment. And like the Green's function explanation, in that case we use a equal 1, a equal 0, and in this case we use 8.625 and 10 for ON ratio. This is a model parameter. And the other model parameter, O2 gas transfer, we use 0.2 and 0.1. And we search for the optimal value for these two parameters. And the optimized value is the right hand side here, 9.243 for 2012 dataset. This means the very small number of BGC Argo case, and 9.091 for large number of BGC Argo case for a ratio, and also gas transfer 0.18, 0.186 is evaluated by this optimized scheme. This is the result from the two optimized parameters. The red shows the ocean state estimation. The black is original model result. This panel shows scatter diagram between model and float observation. The vertical axis is for the ocean state estimation. The horizontal axis is BGC Argo. Right hand side panel shows the large number of BGC Argo, and the left hand side small number of BGC Argo. And the black points is result of model, original model, and the red is state estimation. You can see the red scattering is concentrated close to the linear correlation line. This line. This shows the black model result is improved by this scheme. So ocean state estimation get closer to the observation. And the large number of BGC float show more concentration of red scatter closely to this linear regression line. This shows the large number of BGC Argo data can improve the quality of ocean state estimation. This is another view of our result. This shows the difference between ocean state estimation and BGC Argo float data. When the difference is small, the quality of ocean state estimation is very high. And the horizontal axis is difference, and the vertical axis is a depth from sea surface to 3,000 meters. And these blue curves show the original model result, before optimization. The red and yellow is the after optimization. By using large number of BGC Argo data is red and yellow is a small number. You can see the difference is significantly reduced in the case of large number of data. It shows the subtle impact of BGC Argo is very efficiency when the number is increasing. So more BGC float data works better to optimize the estimation. This is one of our results. The distribution of dissolved oxygen. The upper panel shows a model result with conventional model parameters, and the lower panel is our state estimation, which is the model result with optimized model parameters. You can see the distribution is changed apparently comparing with this result, and the state estimation is improve the quality of ocean state. The improve mean the difference between a model and BGC float data is reduced. So input data, BGC Argo, and physical data, Argo data, and satellite data, and also the other shipboard data makes one dynamically consistent data set. It will be useful to analyze the mechanism of many oceanic phenomena. And this is the other view of more deeper depths at 300 meter and 1000 meter. You can see also the improvement of the distribution, and at the 100 meter, 1000 meter depths, the difference is very small because the variation is very small. I will summarize my talk. Dynamically self-consistent state estimation for BGC parameters along with physical parameters is a powerful tool to clarify the mechanisms of oceanic changes. We demonstrated the BGC float data can improve the quality of state estimation straightforwardly. The improve means the difference between observation and model results are reduced. We made one dataset consistent both with observations and model formalisms. Observations include physical and biogeochemical parameters. It is a promising approach which will enable us to resolve global ocean issues. More research development along this line will be needed because our state estimation is far from perfect. So we keep trying to improve the quality and the data synthesis method. The data is open on the following website. Please use it and give us a comment. Lastly, we sincerely appreciate giving us this great opportunity to promote BGC research. We would like to thank GO-BGC and the G7 FSOI members. Thank you.